Battery Technology with James Kaschmitter. You are listening to Brothers of the Serpent podcast.
And welcome back, ladies and gentlemen, boys and girls, angels and demons and monsters and serpents. This is Brothers of the Serpent podcast, and we are coming to you not live from the 10 by 10 by 10 tangent cube of science, where we are nestled amongst the dusty bones of an ancient seabed high atop the Everest Plateau. And we have a special episode for you today. We are joined by James Kaschmitter, who is the CEO of SpectraPower. He is a battery expert, and so we're going to get him on the show to explain to us how batteries work. We're all interested in this because of, how did people start carrying around electricity with them, right? Batteries are important for that. And we all know, about the Baghdad batteries, but James is an expert in lithium-ion battery technology. Is that right, James?
Correct, yes.
All right. Well, welcome to the show, man. Thank you very much for coming on.
Thank you. Yeah. My pleasure. Thanks, Russ. So I'll pull up the screen share, I guess. And,
sure,
go into the launch into the presentation. Let me see. So how's that? Is that
okay? Good, yep.
Okay. It's James Kaschmitter. Just to get it right. So I have a battery research company in Livermore, California, SpectraPower LLC. Going to talk about lithium-ion batteries, but kind of with a perspective on sort of features, benefits, and issues with lithium-ion. I'll just give a brief background on my background. So I started working in lithium-ion at Lawrence Livermore National Lab in 1989. I was a power engineer for Star Wars orbital platforms. And so we started building lithium-ion cells in 1990. Along the way, started a company, you can see down here, called Polystore, first U.S. manufacturer of lithium-ion cells here in Livermore. And we built all different form factors, cylindricals, prismatic polymer cells, and high-power automotive cells. We introduced nickel cobalt, the first in the world, back in about 1999. Along the way, in 1993, set an altitude record for a solar electric airplane developed by Lawrence Livermore. My group and I did the solar panels for that, set an altitude record of about 83,000 feet. And you can look up Helios. It later went to 100,000 feet over Hawaii. That was about 98. Also started a supercapacitor company, Power Store, in 1997. Fuel cell company in 2002, Ultracell. Those are used by the military in remote power locations. So today, I have a company called SpectraPower, and that's just a picture of our facility. We do contract research and development consulting in the battery industry. So let's see. So I'm going to go through kind of at a high level description of lithium-ion cells. I do give two tutorials at two major battery meetings. One's coming up in Las Vegas here in December, and another is the International Battery Conference in Florida in March. That's probably the oldest battery conference in the U.S., and so these are both very good practical conferences if you're interested in learning more about batteries, especially lithium-ion. I like to show this little video just to kind of
Genius.
Anyway, the problem with donkeys is they emit methane. Anyway, so this is some terminology as I go through here, and so people confuse the term, or I guess cross-use. It was the term battery pack versus cell. So in the industry, a cell is an individual unit. It's I say electrochemical couple. It's one just think of it as like one individual battery. But in the industry, we use the term battery and pack to mean a bunch of interconnected cells. So in your cell phone, you have a single cell, and in your EV, you have a very large pack. And so over on the right here in the picture, I show, everybody knows what the AA looks like. We call it a 14500. So the first two digits are the diameter in millimeters, and the second 650 in this case are the length of the cell in millimeters. The extra zero sometimes gets thrown on for no good reason. Tesla takes it off because they didn't have a reason for it. The first lithium-ion cell, well, actually, most of them were 18650s. This is I don't know. Can you see stuff? This is just for interest. This is the first commercial lithium-ion cell, Sony cell. Believe it or not, the cell is still good. You can see, and it's a different form factor than an 18650, which is here.
Oh, okay. Yeah, I see it.
Yep. These were put into. This is an actual working cell. Before they were available, I got this out at through the government, and they were put into camcorders. So that was about like 1991. So anyway, that's the terminology for that. And the other thing is we'll talk about capacity, energy, and power. And I just want to clarify, because people use energy and power interchangeably. So capacity is typically in a cell is measured in amp hours. So if a cell is 1 amp hour, it means you can put out 1 amp for 1 hour.
Okay.
And it just scales accordingly. So if it's 2 amp hours, you can put out 2 amps for 1 hour. So just like that. And energy is actually the capacity times the voltage. So 1 amp hour cell times 1 volt gives you 1 watt hour. And so I say nominal voltage because if you look down here in the right, you can see this is a typical discharge from a lithium-ion cell.
So you get voltage drop over time.
What's that?
You get voltage drop over time.
Well, it's discharging.
Yeah.
If you didn't discharge, it would stay flat. So this is a discharge curve. And you can see down here the capacity in amp hour, and these are at different rates. Let me explain rate, and then I'll show you this curve more. But you can see how it's, as a cell discharges, the voltage drops from it drops instantaneously to about 4.1, and then just as it discharges goes down to about 3 to 2.8 to 3 volts is about the lowest you'll get any energy out of it. So the nominal voltage is, you'll see it referred to on battery packs when you buy products. It's typically about 3.6. It's sort of the midpoint voltage and the cell's discharge. And then power is amps times volts. So in this case, it's a watt if you have 1 amp, 1 volt. That's different than watt hours. So energy means kind of how much you have in your gas tank, if you will, if you compare it to a car. And power is how quickly you can use that up. So if you have a big engine that burns a lot of gas and goes fast, you have higher power. But you're going to have the same amount of energy in this case because it's in gasoline. In a lithium-ion battery, it doesn't work quite that way. And so that brings us to what is C rate, which is commonly used terminology in the industry. And so probably the easiest thing to do is look down here and see 1 C for 1 hour, that's a 1 C rate. So if you discharge the cell, say at 1 amp for 1 hour, that's 1 C. Now, if you up the rate of discharge to, say, 2 amps, then that becomes a 2 C rate, and it's good for 30 minutes. So it's just how quickly you're discharging the energy in the cell. And this has a big impact, especially in electric vehicles. And you can see here in these curves, these are at different rates. So 0.5 C, which is a low rate, and going up to, I think the highest is 6 C, which means you're discharging it in about 12 minutes. Whereas at 0.5 C, you're discharging it in 2 hours. So this has a big impact on lithium-ion batteries. And you can see just the difference at 0.5 C, you get much more energy than you do if you discharge at a really high rate, like 6 C. So in designing a lithium-ion battery, using these different, you have to design the cell for the rate that you want to achieve. So cells are typically broken into power cells versus energy cells. And a power cell is designed to discharge its energy in a short amount of time, whereas an energy cell is designed to maximize how much energy you can store. So in a laptop, you'll typically have an energy cell, and in a cell phone, because you want to have the longest talk time possible. But in an EV, you have a balance that you have to achieve where, when you accelerate away from the stop sign, you're going to be discharging at a high rate. And that can go up to like 3, 4 C. And then when you settle down into cruise, at 40 miles an hour or something, the rate's going to drop dramatically, and that will give you much more, allow you to use the energy in the cell much better. Is that?
Yeah. So the cars use a combination, or is it just that the cells are designed for like a little bit of both?
It can be both ways. The better example would be a hybrid vehicle, like a Prius.
Mm-hmm.
The battery is doing the acceleration, and regenerative braking, is recharging the cell quickly. And so they have a high rate cell, and then they have the gas engine. In an electric vehicle, it really usually a cell is designed to kind of operate under both conditions.
Okay.
High power and high energy. But as your battery pack gets bigger, your effective rate gets less. And so when you have a very large pack, you're going to get a lot of power for free, so to speak, because you have a big battery that the amount of you're discharging is a smaller percentage.
Yeah.
So it changes your C rate.
But so the other question I have about this is, do you actually, it's less efficient at a higher discharge rate, so you're like not getting as much total energy out of the battery? Is that true?
Yeah, that's true. Let's refer to it on the cell basis. But no, that's very true, because think of the battery as having a resistor in it, just the internal resistance of the cell. And so when you up the current, you're generating more heat through that resistor,
right,
and you're losing energy in that heat.
Okay.
So when you try to discharge it at a really high rate, that can create problems in the cell, but also you won't get the full energy out of it because you're losing some of your energy as you do that high rate discharge.
Okay. That makes sense. Cool.
Okay. Mm-hmm. So let's see. So then a question that gets asked, and I'll talk a little bit just about an overview of where lithium-ion fits in the history of batteries. So this is energy density on the left in watt-hours per kilogram. And that's commonly used. People refer to two kinds of energy density, usually gravimetric, which is watt-hours per kg, and volumetric, which is watt-hours per liter. So that's how much space it takes up versus how heavy it is.
Okay.
So you'll see those terms used quite a bit. So we'll start back here. Lead acid batteries invented in 1859, and then actually NiCads almost at the turn of the century, right about when the first cars were electric vehicles, right? And but really these were pretty primitive, and there really weren't major markets for them, especially as the world went over to gasoline vehicles. So the alkaline, which is your standard primary non-rechargeable battery, like a Duracell Energizer cell, that was 1949. Metal hydride came along after that, about 1975 timeframe. And then in 1992, Sony introduced the first lithium-ion cell that I showed you previously. That's 100 watt-hours per kg, roughly. And you can see over here how energy density is very slowly going up. Lead-acid batteries for a long time were stuck in sort of the 30 to 50 watt-hour per kilogram range because lead is so heavy. And then after Sony introduced the first lithium-ion cell, then things started to move, pretty quickly, especially as, Apple introduced iPods and iPhones and those types of portable devices. It really grew the market. Then they went into laptops. By the way, one reason old laptops are thick is because they had an 18650 lithium-ion cell, so they couldn't make that any thinner. And Apple actually really pioneered the use of the polymer pouch cells that we'll talk about, because that enabled them to make laptops very, very thin. So anyway, that brings us up today. We're running about 250 watt hours per kg is about where the Panasonic cells were in most Teslas, and we're seeing cells now commercially that are running up over 300 watt hours per kilogram, and that continues to improve. And you'll see some claims of cells up to 500, but those really are not practical yet. So anyway, that's where we are there.
And is there, I assume there's probably an upper limit to this. You would have to, is it the idea to shift to some other completely different process, or,
so lithium-ion capacities have been going up at about 5% a year in terms of the energy. It seems like that's kind of where we're at there. You'll see a lot of discussion of solid state and lithium metal batteries. Lithium-ion was actually invented to solve the problems with lithium metal, the safety problems. Lithium metal is, highly reactive. We'll talk a little bit more about that. But, we're really going to have to shift to a different chemistry. I think we'll continue to see, these 5% a year kind of numbers, but it is kind of leveling out. I don't think we're going to see a Moore's law kind of a situation for lithium.
Yeah.
So I just wanted to point out then, this is kind of the timelines for rechargeable technologies. So, here we have lead acid gets commercialized, and then it's mature. And it's, it's still around today. It's, sort of in this 56, maybe 60 watt hour per kg. There's been some improvements, but nothing dramatic. NiCad came along as sort of the first portable cell, and achieved some commercial success until, people realized that cadmium is a heavy metal poison, and when you put it in a landfill, it ends up in the groundwater, and your kids are born with 3 arms and legs. And things like
Jeez.
So it's been phased out in definitely in Europe and in most places. It's still used in a few niche markets, but I think even there it's dying off. So metal hydride came along, and it's around 120 watt hours per kg, and it was really designed as a replacement for NiCads, both because NiCads have this memory problem, and metal hydride is higher energy density. It kind of got killed. It was going pretty strong, and then it kind of got killed when lithium-ion came along, because the energy density in lithium-ion was so much higher, and other performance parameters. So, lithium-ion development started commercially at Sony in about like 1980, and they were able to introduce it commercially in about 91, 92. I think 92 is when it really kind of came onto the market widespread, and so it's continued to go to this day. The reason I started working in lithium-ion is that when I was looking at cell chemistries for use in satellites, you know, most of the battery chemistries were pretty primitive and performance was pretty low. We actually did some test flights with metal hydride cells, but, quickly switched over to lithium-ion. When you're launching a satellite, weight is so critical. It's up to about $15,000 a kg to launch, something. So it's extremely expensive. The downside of that, though, is the lithium-ion safety problems, and we'll talk about that. And then lithium metal, and I'll explain more about lithium metal in the next slide, can give you much higher energy densities, but it has some real, safety issues that have to be resolved, which is why people have been pushing to solid state, which is basically lithium metal with a hard separator to hopefully solve the safety problems.
So don't like gas powered cars still use lead acid? Why do they do that? Why haven't they changed to a different battery type?
Cost. Really? The battery. People don't talk about it, but in the battery industry, the biggest single thing is probably cost. In terms of any parameter. And lithium ion has historically been expensive. It's hard to make, and I'll show you why. That has enabled lead acid to kind of survive that, and the fact that it's designed in to so many things. And it also is, I think, one of the most recycled things on the planet. Surprisingly,
car
it's
batteries?
like over 95% of lithium, of lead acid batteries are recycled.
They give you a good chunk of change for bringing that core in.
Get the core discount. Yeah.
Nobody wants to lose the core discount.
Yep. No, and that's why that's one of the reasons for its success. And it also is an example of what you can do with recycling when you really want to, get serious about it.
Yeah.
So,
man, I'd
those
love
things
to
are
have
freaking heavy though.
I know.
It would be great to just have a light.
But lithium.
you can buy lithium ion. So iron phosphate, which is the cathode in some lithium ion cells, has a flat discharge. I don't know if I have a picture of it, but anyway, it makes nice 12-volt battery replacements because of that. Lead acid has quite a flat discharge, and which makes it easier in terms of using it in a circuit.
Right.
And so that's one of the reasons. Plus, they're simpler to charge. Lithium-ion has a more complex charging mechanism. So as we go through the battery world, we should listen to our elders. So Thomas Edison was famously quoted. So the storage battery is also known as a secondary battery or a rechargeable battery. And he said it's one of those peculiar things which appeals to the imagination. Nothing could be more desired by stock swindlers than that. just as soon as a man gets working on the secondary rechargeable battery, it brings out his latent capacity for lying. And I'll talk. So it's a word of caution, I guess, as we go through this. So this goes back to 1883, and we've sure seen some of that. And the reason it's so, I don't know, seductive to talk about battery specs is they're so multidimensional. And this is just a chart I pulled because it's pretty illustrative, and it's got nickel zinc on here, which is another system. Anyway, we won't talk about it, but so you can look and see. So here's all the different parameters. So I mentioned cost. That's very high on the list. Cycle life, how many times can you recharge it? The energy density, toxicity is an issue, like cadmium. Recycling, how hard is it to recycle? Lead acid's pretty easy. Lithium ion, not easy. At least not easy in an economically viable fashion. Safety, not good. Not very good. Power density, Can be pretty good for lithium-ion manufacturability. They're hard to make. So you can see
Wow.
like each of these different parameters. And so I think this group was making nickel zinc, but it has other issues, so we're not going to talk about it.
Yeah, they just look at how good it is.
Yeah.
And they hide the places where it's bad under the other stuff.
Yeah. And he doesn't like lithium-ion because it's what everybody uses. But, you can see, like look at lithium-ion in the gray here, right? Really good cycle life. It's expensive. Energy density is the best there is. Toxicity, not that bad. Hard to recycle, safety, not too good. Good power density, hard to make. So you can see, if you're like selling stock, you can ignore the cycle life and the cost and just say, oh, it's got this great energy density, and you can ignore the safety and just say, gosh, your car is going to go 10 times further, but well, it's super expensive, won't last very long, and it might blow up. So it's fertile ground for people to talk about the things they like. So anyway, so let's talk a little bit about how a lithium-ion cell actually works. So this is on the left is your sort of high school chemistry, pictorial of a lithium atom. So there's three in the nucleus, typically 3 neutrons, 3 protons, although actually in nature it's more like 4 neutrons, but that doesn't matter for a battery. And then there's 3 electrons. So there's 2 in this inner circle, if you will, and then on the next orbit out, there's typically 8 in that orbit maximum, but in lithium-ion there's only 1. So the inner circle takes only 2 to fill its orbital, so it's happy. But when you have this 1 electron out here, it's think of it as kind of lonely. It really is looking to have 8 electrons in this orbital. So what happens is it makes that the lithium very, very reactive. It's fun stuff to play with if you're careful. If you take a chunk of lithium and throw it, in a swimming pool, you'll have a depth charge because it'll explode underwater.
Wow. Great tip. Thank you.
Yeah, don't do that at home, but it's fun. It burns extremely hot, though it is dangerous. I really should seriously say, it's really neat stuff because it's so light. You hold it in your hand, you can't believe that you're holding anything, and
wow,
and it's so malleable. We take it sometimes. We'll just roll it out into sheets. It's just almost like silly putty or whatever,
Wow.
gum or something. But it is dangerous because this 1 electron either wants to pick up more electrons in its shell, or it wants to get rid of this electron. And so this is lithium metal in this form. When you take away this electron, you have lithium ion. And as I mentioned, see, when you do that, this lithium ion this inner shell is satisfied. Yeah, so you don't. It's a little bit more stable in a cell, and but lithium metal has all of these. Is this full atom as we see it here? So we'll talk about how that works. This is what makes lithium-ion work the way it does. I should also mention sodium. It's in the next up in the next column in the periodic table, and you can see the atomic number is 11 versus 3. Mass is 23 versus 6 or 7 for lithium. So you can use sodium in a lithium-ion cell, and there are sodium-ion cells being introduced, but they don't have the performance. But you can see they'll be heavier, and it's a bigger atom. So you won't have volumetric and gravimetric energy density that you do in lithium-ion. Anyway, just so that you'll be seeing more on that. So this is kind of a key slide to understand. Let me just turn that off. How a lithium-ion cell works. So up here you can see our little Duracell battery symbol. So on the right here is the positive electrode, and on the left over here is the negative. In between is a porous separator. Separator just keeps the two electrons from shorting. So it's a critical component. So when you build a lithium-ion cell, you build it in a discharge state. So over here this is lithium cobalt dioxide, which is very common in portable devices like cell phones because it has the best volumetric energy density and very good gravimetric energy density. But it has a complex structure, and you build the cell with lithium cobalt dioxide. So the lithium is in the cathode. So just think of cathode as positive and anode is negative, by the way, on a cell as we go through, because out of habit, I'll be referring to them as cathode and anode. So, but people think of it as positive and negative. So you build the cell with the lithium and the cobalt and a little bit of lithium in the electrolyte. So the electrolyte is typically a carbonate. We call it. It's carbon-based electrolyte, diethyl carbonate, dimethyl carbonate, things like that. And they're usually mixed combinations of electrolyte, and it's most often in a liquid form. And then over here on the left is the anode, and that's graphitic. So it's a graphitic carbon. Now, in both cases, these materials are coated onto the surface of a current collector. So in the anode, that's copper, and I mentioned real thin copper foils, state of the art 6 going to 4 microns.
Wow!
And for people, that's like a tenth of a human hair kind of number. Very hard to handle. And on the cathode, it's aluminum foil, and that'll typically be more like 10, 12 microns thick, still quite thin. They're high purity foils. The copper foils electrodeposited to make it, and I think the aluminum is probably rolled sheet.
It's copper deposited onto graphite? Is that what you're saying?
The other way around.
The copper foil itself is made through electrodeposition. So you mix copper in a solution in a bath, and then you basically submerge a drum in that and charge the drum such that the copper slowly plates onto the drum, and then you peel it off to make this really thin foil. So
then you encase that foil in the graphite.
You fold it or something, or how does it work?
You coat it. So you take this graphite powder and mix it. You mix it into a slurry. Most people use water to make that because it's cheap. And when you make it, there's no lithium in it, so you don't have to worry about the water. When you coat the cathode, you use something called NMP, N-methylpyrrolidone, which is an expensive solvent, but because there's lithium in the cobalt, it doesn't react.
Yeah.
It's also volatile. It's hazardous and flammable. So you have to be careful about that. The electrolyte is notable too, in that it's actually very flammable. It's I've seen it referred to as similar to, not quite gasoline, but it is highly flammable. So when you are carrying around a lithium-ion cell, on a very approximate level, the chemical energy just in the components, mostly in much of it in the electrolyte, is flammable, and it's about the same amount of energy as the cell. If you take like a laptop battery you can be talking about, some percentage of a stick of dynamite of energy in your laptop.
Wow.
And in a car, you're talking about a lot of sticks of dynamite.
Yeah.
It's crazy.
So, there's a lot of energy. You're storing this energy, right? And it's got to be somewhere. And that's problematic because, carbon is, it will burn. Think of charcoal, right?
Yeah.
And so you've got some, pretty reactive stuff. Now, in the electrolyte, the solvent, which is the basic solution, has impregnated into it or mixed into it, I should say, LiPF6, lithium perchlorate, which is, think about it, is lithium, phosphorus, and a lot of fluorine, 6 fluorines. Fluorine can be very, very hazardous, and one of the hazardous things in lithium-ion is it can combine with hydrogen and make HF, hydrogen fluoride, which is extremely dangerous. It will literally penetrate through your skin and dissolve bones. Chemists, it's one of the things chemists are really scared of. It's very, very reactive, and anyway, so it's very dangerous. And the gas, if you breathe it, is also very dangerous.
Oh yeah.
So,
but this is what you get with any sort of power source, right? It's going to be dangerous, and if you're packing it in really as small as possible
with a high energy
with an
density,
enormous amount of power, then yes, it is basically a bomb.
Yeah. Well, anytime you're storing energy, you've got a lot of energy there.
Yeah.
And you're trying to keep it contained, right?
Yeah. It's like a battery is basically like, let's make a bomb and then have it go off really slow.
Yeah.
Well, people talk about using them as bombs.
Yeah.
But so let me explain the charge and discharge. By the way, so I described the anode and cathode. The separator is also critical. It's typically it's either mostly polyethylene, sometimes polypropylene, which are very inert, plastics. Very thin sheets down to about 5 microns. That's all that's keeping these electrodes from shorting.
Wow.
And polyethylene also has a negative feature in that it shrinks and melts at a fairly low temperature. So one of the problems is if these cells get too hot, then this polyethylene can be close to where it might start shrinking. And when that happens, you're losing separation and can cause a short. The other thing that can happen is when you move the lithium, well, let me explain it, and then we can talk about it. So we build this cell. Let's start with a cell that we just built. It's discharged, so 0 volts. What we're going to do when we apply a charger, and that's what this little V is shown up here, is that all the lithium sitting in the cathode, we're going to take and apply a negative and a positive here, and cause the lithium ions to get pulled out of the lithium in the cathode, and they're going to get moved back through the separator into the graphite. That's the charging process. So what's going to happen is the electrons are going to get stripped by the charger and pulled over into the anode, which makes that a more negative charge. And so the lithium gives up its extra electron in the outer shell and moves over into the graphite, where the process is called intercalation. And what happens is it goes into these graphite rings, if you will, and picks up. It's stable there because that electron that it left over or gave up over on the other side, it picks up over here and is in a stable chemical configuration in the graphite. This is why lithium-ion has such, one of the reasons it has such low self-discharge. So, I have lithium-ion cells that are 30 years old, and they still have charge.
Wow.
Which is phenomenal compared to other battery technologies. And so one of the reasons is that these ions are stable. in these in the graphite. So
that going back to the lithium atom, that's, you were saying that they really want 8 electrons, but the ones you're talking about, like typically they'll have 1 extra on that outer shell, and then you strip that away so that they don't even have anything on the outer shell once you charge it.
Yeah, and so as I said, it was lithium-ion was invented to solve the problems with lithium metal, because lithium metal cells have been around for a while, but you have this sheet of lithium, pure lithium, and it's, if you puncture the cell or anything, you're going to have an explosion.
Oh,
and that's why lithium-ion, and actually it was Sony that commercialized lithium-ion, so they kind of developed the whole system. If you look at the Nobel Prize that was given for lithium-ion cells, John Goodenough and some of the other guys, they invented components. Goodenough was critical in the cathode, the cathode is the most difficult part of a lithium-ion cell to do. That's why whenever you look up cells, you see them called out by the cathode. This would be an LCO cell, lithium cobalt dioxide. But anyway, when these ions get moved over here into these graphite, they're in a stable configuration, so it's safer in that regards. It doesn't mean the cell is perfectly safe. It just is safer than if you had, say, a big sheet of pure lithium metal sitting over here.
Right.
So, so then let's see. Oh, the separator, by the way, these are very inexpensive materials: polypropylene, polyethylene. Polypropylene's like, I think, milk jugs. It's a very stable plastic, but it's microporous, and so the separator, you can see kind of here, looks like a sponge, and it's an open cell pore structure. It's infused with electrolyte, flooded with electrolyte, and so the ions are moving through, the lithium ions are moving through the electrolyte, through this pore structure. That's how they get to the other side when you charge the cell. So then we have a charged cell. Now, if you want to discharge the cell, what you do is you put should show, but think of it like a resistor here. That's your load. And what happens then is these electrons go through the load and back over here into the cathode. And so the lithium ions, are giving up their that stable electron configuration. So they're pulled back through into the cathode. And so then that's your discharge state for the cell. And the cathode, typically, to maintain structural integrity, you can't take all of the lithium out of it. And so some of it's left there. And you can see in this kind of complex crystalline structure, where you have, even after you fully charge a cell, you have some residual lithium. Now, one of the most dangerous situations for a lithium-ion cell is overcharge. And the reason is that, you're going to go up to about, typically for cobalt, 4.20 volts is your maximum charge voltage. But if you go over that, say you go up 5 or even 10 volts, you're going to pull all of these electrons out of the structure in this cathode. You're going to weaken the structure of the cathode. When that happens, it basically starts to dissociate. It's got oxygen in it, and so you've got oxygen and lithium, and the cell, if you keep overcharging, it will explode. If you overcharge it and it doesn't explode, then you have a very dangerous cell, because you've got the cathode basically dissociated, broken down. So it's
literally changing its physical structure, like the molecules start disassociating from each other, the crystalline structure.
Yeah, it breaks up.
Wow.
And
so this is why all the lithium ion cells have to be charged. They're smart charged, right? There's there's a controller.
Yeah, so you typically will charge you'll specify the C rate that you're going to charge at. So if you're say a 1 amp hour cell, which is, in your cell phone, you've got about, I think 3-4 amp hours if I'm up to speed these days, but you're going to charge it typically one half C rate. So maybe it's a 2-hour charge. If it's a laptop and it's a high energy cell, your laptop takes longer to charge typically, right? It's more like 4 or 5 hours. And the reason is that it's at a lower rate because you have a high energy cell. And so anyway, the other thing is, by the way, is if you pull this charge out too fast and you try to charge the cell too quickly, you can cause a problem, because the lithium, this intercalation process is a physical process. If you remember, like pencil lead from school and stuff, it's kind of flaky, right? I don't know if you ever played with graphite. And it's those planes that the lithium's going into. And so the morphology, in other words, the shape and structure of this physical structure of the particles is important, especially on the anode here. So if you have big particles, which might give you higher energy density, well, it takes longer for the lithium to intercalate into the particles because it's actually moving into these planes physically. And so the bigger the particle, the further it has to go to get into the plane of the graphite. So if you try to move it too quick, then what will happen is what we call polarization. And when you think about it, so these particles, these lithium ions, when they come up to the graphite particles, they don't just sort of hop into it. There's actually a pretty complex transformation, if you will, where the lithium has to migrate through what's called a solid electrolyte interface. SEI layer is how it's referred to, and that SEI layer is really critical for safety. I don't show it here. I have it, I think, on some other slides, but I'll just explain it. Because that's how the ions move, from the electrolyte solution into the solid graphite. Now, if you try and move them too fast by applying, a lot of charge quickly, they bunch up. Think of it along the side here. They bunch up against the graphite particles, and because they can't all get in at once. It's like the mob rushing to the door to get out or something. And they also, they're both positive charges, so they're repelling each other. And so what happens is that it'll just stop charging because there's too much charge at one time. If you remove the charger, then you'll see sometimes it'll relax, and so the voltage will change. Now, if you do this on discharge, you'll see this actually sometimes in your portable devices. If you look closely, like a power tool, you'll move all the lithium ions out of the graphite on a discharge and over to the cathode. When they get to the cathode, if you've just shorted the cell or put a real high load on it, the lithium ions will bunch up here because they can't get into the cathode quick enough. And so what it'll look like is the cell's dead. But then if you wait, sometimes, for minutes.
Give it a couple minutes. You'll have
more
power.
It came back. What happened, right?
Yeah.
And there's much there, because when you try to use it, it goes dead pretty. But that's the polarization effect. Because,
that's awesome.
Wow.
Yep. So I've noticed that in drills, like power drills and all that kind of stuff. Like you'll be using it and it just dies, and then like you put it down for a minute or two, you pick it back up, still going. Like, all right. Yeah. That's awesome. Thank you for that explanation.
So that's what's going on there. So let's see other things. We'll talk. There's some issues regarding safety to it, but we'll talk about those in a little bit later slide. So that's kind of the the fundamentals of how a lithium-ion cell
Is it correct that the last, say, 10% of the charging takes much longer because those ions it takes a lot longer to find a spot in the lattice over there?
Yeah. So I was going to mention that too. So typically the charge cycle for lithium-ion is constant current to constant voltage, CV charger is what you'll see. And so the constant current is a specified rate, and it holds the current at that rate. So in other words, like I say, if you're going to charge at 1C in a 1 amp hour cell, well, you'll apply 1 amp. You'll limit the current to 1 amp. So it can't go try to charge too quickly. One of the biggest safety problems you can run into is if you try and charge too quickly, you can plate lithium metal onto the surface of this anode. And it's actually a pretty common problem. We take apart lots of cells, and it's not unusual to see lithium metal plated in spots.
Wow.
Because if you think about the electrodes, they're not perfect. So there's some spots higher, some are lower. And so if you have a thin spot on your electrode, there may not be enough room for the lithium to get in. So it just ends up plating onto the surface and forming lithium metal. You can see it because it's a silver looking material like lithium. That's one thing you have to watch out for. The other thing that is a common problem is low temperature operation. And this electrolyte is just like the oil in your engine in terms of when it gets really cold, the oil gets very viscous and sluggish, right? When you try to crank it, it's rrr.
Yeah.
You guys in Texas don't have that problem, but
Nope.
there are
Not
people
usually.
that do. And especially like EVs in cold climates. And you don't want to try and charge a lithium-ion cell when it's really cold. And that's, like 0 or 10 degrees, Fahrenheit and stuff like that. And especially when it gets real cold, because this electrolyte, it can actually freeze. And, but at the very least, it becomes very viscous and very, thick, and the ions don't move through it well. You'll notice it's actually a pretty dramatic effect. I have an electric motorcycle, and on a hot day, it's a lot faster than it is on a cold day. And it's because the electrolyte thickens and the ions can't move through it. But the really bad thing about trying to charge a cold cell is that the ions can tend to bunch up on the anode and plate lithium, and so you'll see the typical operating range for lithium-ion is 0 to 45 centigrade. And the reason that 0 is important is you get below that, and you don't want to be charging the cell down there. So, I get people like from Minnesota that have asked me, like, well, what about charging it, outside at night? And I'm like, don't do that. No. It's a bad idea.
You're just plating you're making a bunch of lithium metal inside on the anode.
You're making your cell unsafe. And
oh my gosh.
Isn't there like couldn't there be some kind of solution, like, include in the charging system, like some kind of warmer, so you plug the charger in and it warms the battery up and then charges it?
Yeah, exactly. So in an EV, you'll see modes where I forget the term, but it's basically preconditioning.
Yeah. Okay.
What they're doing, so when you discharge the cell, remember it's like a resistor inside. It's going to self-heat to a certain amount, but what they have to do is get the pack warm enough before they start, charging it. Because when you charge it, you'll generate heat just by the resistance in the cell, moving the current through the resistance. And so they precondition to get it warm enough so you don't have a safety problem, and then they may vary the charge rate to allow the cell time to warm up.
Yeah. Okay. Cool.
Yeah. So let's see.
Should we? I I know before you go to the next slide, should we take a break? Something went wrong with the light there.
Yeah,
Sure. Okay, we're back.
You got the video going?
I do.
Okay.
Okay, now we'll get to do our safety.
Oh. Oh.
Jeez.
Yeah.
Holy crap.
That one, I think it really gets the message across.
Bomb bikes.
I've seen a bunch of videos of that. There was one I thought of a guy who he dropped he dropped something on his cell phone and it started to flash, and then just basically exploded.
Yeah.
Yeah. Like crushed the battery and.
So there's a little bit of warning. When you start seeing sparks come out of your phone, just run.
Yeah.
Okay? Like don't
throw
try
it and run.
don't try to do anything.
Well, it's like EV fires. There's really nothing they can do. They douse it with water to try and keep the heat from the cells propagating to the neighboring cell or whatever.
I think water might, like if there's lithium plating in there, maybe dousing it with water could be a bad idea.
It can make it worse. And that's one of the issues with lithium metal is even if it's in a solid state battery. Actually, let me explain. Are you guys familiar with solid state? Have you seen the?
No,
yeah.
I'm interested in that.
So
sure.
you'll see there's some companies that have gone public, and there's a lot of talk about it. Toyota keeps talking about introducing a car with its solid state battery. So what is a solid state battery? Well, what they do is they take in this porous separator, which is just a thin white plastic sheet, very thin. They make that a solid sheet. So it's a solid sheet of plastic or ceramic, and then they put that between the electrodes here where the separator would normally go. Now, one of the problems they have is they're trying to get rid of the liquid in the cell, because remember I said that's very flammable, right?
Yeah, the electrolyte.
And when you have these explosions, a lot of it's due to the liquid kind of getting it started.
Okay.
What you get is typically you'll get like what's called a dendrite, and it'll puncture this separator. So this separator is just a very thin sheet of plastic. Sometimes they'll put a coating of ceramic on the top to try and make it stronger, which helps, but isn't a perfect solution. And so when you get a dendrite, so one of the things we talked about, getting lithium metal forming on the surface of, say, your anode during an overcharge or other situation,
or a cold charge, yeah.
That lithium, when it plates, if you go and then you cycle the cell, you're moving the lithium back and forth. And what happens when there's lithium metal, well, is it plates the metal. Well, lithium doesn't form plated metal very well. In this situation, it's kind of you have to carefully control that process. When you do this, lithium forms what are called dendrites. They're like sharp needles of lithium. And the reason those form is that anytime you have a little bit of a high surface here on this lithium metal, it causes the charge to focus, if you will, into that one point.
Mm-hmm.
And what happens then is it deposits and it builds and builds and builds until you get this very sharp needle. And these things are...
It's like a nucleation site, like a sharp point is sort of like a nucleation site for crystallization or whatever.
Yeah, the field lines focus into that point, and everything goes to that point. And so I don't have any pictures here handy, but I think I do elsewhere if we have time. But these are really sharp little metal needles, and they poke through the separator, causing a short. What happens is that short is like a little resistor. And when it gets hot, the separator tends to melt or shrink around it. So it gets worse and worse, and then it explodes. That's the process.
Yeah.
And a lot of times, most of these explosions are caused due to particulates in the cell that are not supposed to be there, but inadvertently, due to just, errors in production, get into the materials. And when they do, then when the lithium is moving back and forth, it wants to plate onto those particles and form a dendrite. And so the concept of solid state is, well, we'll put a solid sheet of material here that's, hard. And so the dendrites can't puncture it, and you can't get a short. Well, it's not a bad idea, but there are issues with it. And one of the issues is that, well, even if you have this here, the solid, you still have liquid in the cathode. And so people are trying, they're usually kind of cagey about admitting it. Because, it's kind of a flaw in the whole thing. The problem with solid state, people have been trying this for decades, is it's expensive, typically. It's hard to make. If it's like a ceramic, it can be very brittle. If the materials don't want to transport lithium ions because they're a solid, right? Yeah. They're not. It's not sort of in their nature, and so there's all kinds of. There are certain plastics that have certain characteristics that allow them to transport lithium, for instance. But in general, it's a difficult problem, and when you see in the manufacturing slides, what the issues are with manufacturing, well, handling this solid state material is difficult. Making it can be difficult, and then it doesn't necessarily fit into the production process very well, and that's why it hasn't really seen commercial success yet. And the other thing is that, so to justify the additional cost and difficulty, then people typically want to use lithium metal because it gives you much higher energy density. So they replace this graphite, a carbon anode, with a lithium metal, solid sheet of lithium metal. And the idea is, well, the separator will make it safer, and it helps. But if you go puncture that cell, you've got a problem. You've got exposure to lithium metal, and especially like in an EV, in an accident, if you get water in there, then you've really got a serious problem. The other thing is, it typically requires some compression to hold these electrodes together, and especially can be true in a lithium solid state lithium cell. And that it just adds weight because you have to mechanically press these together and hold them in compression. So, it's always funny with lithium ion that there's so few components, but it's such a complex system in many ways, right? and we're not even really getting into the details yet.
And it's also technically no moving parts, but there's a whole bunch of stuff moving around.
Yeah, but I guess this may be more of a physics question, but I don't understand how, like, if it's just the ion, like, if we're talking about an electron moving from one place to another, is that all?
No, it's the lithium.
It's actually the lithium is also moving.
Yeah, the electrons are going out through this wire, right? So think of it as the third electron, the lonely electron. It's going this way, and so the ions are like, then they suddenly have a charge, right? Because they lost an electron,
right?
And so that charge is over here, so it pulls them.
So the ion, the actual lithium ion is moving the lithium itself.
Now, it isn't sort of like it just sort of picks up and walks over there. There's actually, think of it as like a chain of lithium across, because remember, it's permeating the separator, and it's permeating both electrodes.
Okay. So it's in the electrolyte.
Comes in one side, and a lithium pops out the other side. Is probably the way to think about it.
More like okay. Gotcha.
Okay.
Yeah. So it's not like you could say, lithium number 5 has just got up and moved over here,
No, I understand that. It's more like a resonance, almost like this one bumps up here and this one comes and does something on the other.
Yeah, there's a whole complex, if you really want to get in the mud, there's a whole complex theory about how that works. But
we don't have to go there, but yeah, I am actually interested in that stuff.
Yeah. Yeah. no, it's interesting, and now there's so much literature about it. You can find just about anything. So anyway, that's what's going on with solid state. Let's.
So this video you show of the bicycle catching on fire, is he charging it? It happens during a charge cycle.
You can't really tell. I guess that more likely. So they're much more dangerous when they're charging. And this is a kind of a graphic. This is a pretty good one too.
Where to park your EV?
So we're back in China here. So
这是监控下令人不可思议的一幕。右侧这辆新能源电动车突然只冒出浓浓白烟，也就在这时，电动车开始起火了。刹那间火光冲天，这火势实在是太大了。整辆电动车被大火吞噬。大家注意，右侧第二辆电动车也被引燃了。这是不好的预感从我的脑海中浮现。如果在没人发现，估计5辆电动车都要遭殃。此时正处于凌晨6点半，估计大家都还在熟睡呢。这时，第二辆新能源电动车也被大火吞噬，就连一旁的垃圾箱都连带遭殃。此时，第3辆也被引燃了，果然不出所料呀，这可是人家花巨资买的新能源车呀，烧一辆还好，可看着节奏没有人发现。这时，第4辆新能源车也被引燃了，此时的火势是越来越凶猛。在这时，园区内有人发现了，拿了灭火器来，可由于火势太大了，起到的效果也非常小。又过了一会，消防救援人员赶到扑灭了大火。我们可以看到，右侧4辆新能源车都已经被烧报废了，仅剩车壳的主架了。而最左侧的一辆维修一下，应该还可以继续使用。大家针对新能源电动车着火怎么看？
Hey, there was still one good bus left.
I know what he was saying. He was saying, "Do not park your EV next to all the other EVs."
yeah. Well, it propagates, right? The heat. It even caught the dumpsters on fire.
Yeah.
And you can see then. I think they saved the last bus.
Yeah, the last one was still good. Were they spraying water or foam?
I think it was foam. Everything was white all
I think
around.
it looks like a foam, but I can't see. That looks kind of like a foam.
Well, everything was white all around.
I saw that white all around, but I think the first thing they were spraying was water.
Yeah.
The first guy showed up.
Some guy's like, no. Yeah.
So this is what happens. I don't know if I have the picture. There's I have I think a picture later, but there was a ship that went down that was full of brand new cars being shipped from Europe over to the U.S. and it had electric vehicles on it, and the whole ship went up.
Oh my God! Can you imagine? Jeez,
falling into salt water. Yeah.
Oh.
Yeah.
I've never even thought about that. Like packing all those things on a boat.
Yeah, so the EVs took out, all the gas cars and a couple $100 million worth of cars.
Oh, Jesus! Some
pretty exotic cars. So
some insurance company was not happy that day.
Yeah, no, it's a problem for shipping EVs, right, on boats, and I don't think it's really been resolved. I mean, the whole safety issue in general in lithium-ion is still unresolved, and there are things that are helping, but they haven't really completely solved the problem yet. So I was going to talk a little bit about different anode and cathodes just briefly.
Okay.
So there's really two principal anode materials, graphite and silicon. There are some versions of carbon that are mentioned. I won't really go into them much. This is a little bit dated, but it's still pretty relevant. It's the what type of carbon do people use? So most of it's what's called artificial graphite. They take sort of raw graphite and process it. It makes it more pure, and so it gives you better cycle life and a little bit better performance. Then there's what's called natural graphite, which is very, very cheap. I haven't checked the price recently, but it was as low as like $5 to $10 a kg. So very, very inexpensive. And it actually has been sort of being phased out. Artificial graphite's a little bit more expensive, and so it's been taking over. People use it because of the cycle life, I think, is one of the main reasons, which translates to cost. And now you're seeing more and more silicon, and especially like in EV batteries. But you can see here, then this is 5-6 years old. Silicon was just starting to come on. There's also something called LTO, lithium titanate, and it actually is an interesting material, but very low energy density. And then you see amorphous carbons, which were kind of the original carbons first used in lithium-ion, but have really been overtaken by graphite. There's a kind of an interesting story about why Sony, anyway, didn't switch to graphite, but we won't have time for that. Anyway, so here's the chemical reaction in these two materials. So, C6 to LiC6, right? So when it goes into that, it's called a benzene ring on the anode in the graphite, then it forms LiC6. So you've loosely bonded the lithium in there.
Yeah.
That's why it's stable. So that's the intercalation process we talked about. Silicon is a completely different process. We refer to it as lithiation. So basically, the lithium is bonding to the silicon. Now, if you look over on the graphite, you can see you get 1 lithium for every 6 carbon atoms. If you look over on the silicon, you can get up to 15 lithiums per every silicon atom. So huge difference. And that's what this atomic ratio is explaining here. But there are some problems with that as usual. So graphite gravimetric energy, just of the materials, 372 milliamp hours per gram is a typical number. But silicon, if you fully lithiate it, in other words, you pack in all the lithium you can into the silicon, you can end up with, almost 10 times that capacity, which is obviously a big deal.
Wow.
But the problem with it, there's a couple problems, but one of the biggest problems is when you cycle a lithium-ion battery, and I didn't talk about this, but it's going to swell and contract as you charge and discharge. And people don't typically see that because it's made up for in the cell design. But graphite will take up to a certain amount of volumetrically, but it will swell while it's doing it. 7% is a pretty typical number. So on the silicon side, you can get these much higher capacities. It will take out a lot more lithium, but it's going to swell.
Three times
the size.
Jeez.
Yeah. So if you try to lithiate, and it actually can go up to more like 400%. If you fully lithiate silicon, your cell will actually burst open because of the volumetric increase is so large. So there's a lot of work going on. And so right now what people do is put in they mix in 5 to 10% silicon in the graphite. So a lot of the EV cells will have that. One advantage of silicon is its very high rate, especially on charge. So, people will use it to kind of speed up the charging. But they'll only mix in a small amount because it swells way too much. And then they don't fully lithiate it. So the lithium, you'll be down more like, instead of 2100, you'll be down, maybe half that or something. They don't use it at the full capacity. And there are people trying to increase, obviously how much of the silicon they can use. And they do that through a lot of materials, formulations and morphologies and things like that, coatings. But the industry really, they'd like to go to 50 or 100% silicon instead of graphite, but it's not there yet. And those are some of the problems.
Can you? Are there ways? Are they looking for ways to build the battery so that it can just accept the swelling? Like, in other words, the case of the battery itself can hold the different sizes?
Yeah, the problem with that is then it gives up a lot of the advantage, of the silicon, because you have to have a bigger case, which is heavier, that kind of thing.
Yeah. So
what they typically try to do is take care of it sort of on the micro nano scale.
Okay.
Where they allow for a certain amount of swelling in the material. Sometimes they'll encase it or put they put it in with a graphite because it allows some room for swelling. so you don't really see it. But yeah, you see different kinds of, pretty sophisticated methods to try and solve that.
Okay.
Yeah.
I always find this type of stuff interesting on the physics side, where it's like there's this process going on the atomic level or maybe molecular level that like does not care about the resistance of like macro physical objects. Like you could encase this thing in a steel cylinder and it would just like keep adding molecules until it just doesn't, it's like it doesn't notice the that resistance against that volumetric expansion.
Well, it's going to swell. So there have been cases of, this is an 18650. This is I'll talk about it more, but it's a steel can. It's nickel plated steel, and it's a pressure vessel. So it'll take about 1,000 PSI before it bursts.
Wow. And
so if you overcharge silicon in a pure silicon alloy, it will burst this can open. So
no problem.
It's definitely a physical process.
That's wild. Yeah.
Yeah.
Very interesting.
So these are that's just a list of cathode materials, because that's what people typically hear about. So we mentioned LCO, lithium cobalt dioxide. So it's mostly used in consumer electronics. Cobalt has this issue. We'll talk about mining and stuff, but the price, and I'll show you the pricing, it's very sensitive to the cobalt price, obviously, but it does give you very good, probably the best volumetric energy density you can get. So like in a cell phone, it's desirable because it's got good energy density from a weight basis, and it's also got good volumetric, so your battery doesn't get too big. Then there's something called high voltage LCO. Basically, the material is processed sometimes with coatings and things that allow it to go to higher voltage. And so here, the traditional LCO cells 4.2 volts max, and with high voltage LCO, you can go as high as 4.45, and it actually gives you quite a bit of advantage in energy. And then there's NCA, nickel, cobalt, aluminum. This is what Tesla uses for their cathode. And so it's about 80% nickel, 15% cobalt, and 5% aluminum. The aluminum is in there really pretty much to help the safety. But it's a little bit tricky to handle in manufacturing because it wants to absorb water, and so you have to be careful handling it. And safety-wise, because it's got a lot of nickel, it's not. I would say safety we have low. Don't think of it as unsafe. It's just not as good as some of the others. And then back in about 2008, actually, I think I can show you on another slide. Cobalt price went crazy. Went up by a factor of 3 or 4. And so the industry switched to what's called NCM. It's nickel, cobalt, manganese. And these numbers, 622 and 811, are the relative ratios of how much nickel versus cobalt versus manganese is in material. High amounts of nickel tend to make the safety worse. I can show you more on that. And so 811 is fairly recent, within the past few years. When it first came out, it had a lot of problems, unlike 622, which is very stable. And anyway, recently, 811 has gotten dramatically better. That's due to some of the Chinese manufacturers. And it's now actually a very, very good material. So you can see in terms of energy density what it does. So it's somewhat comparable to NCA, but it'll take the cell energy density up to the high 200s range, whereas N622 is more like 220. Then there's iron phosphate, which is really you use a lot in power tools, and in China they use them in EVs quite a bit. It has much lower energy density than these others, but it has some advantages. So there's no nickel or cobalt, which are materials that are expensive and potentially rare. It's iron, phosphate. So it's F is for Fe, iron,
Yeah.
and P is for phosphorus. And so it doesn't use exotic materials, or it's not sensitive to nickel cobalt pricing because it's lower energy. It tends to be safer, and the way they design with it is for high power, and that's why you see it in power tools. And then there's a couple. LMFP is interesting because it's an effort to improve the energy density in iron phosphate by raising the voltage. So iron phosphate has typically a lower, this 3.65, is the max charge for iron phosphate. Typical discharge voltage is around 3.25, 3.3. And if you put in manganese, you can get up to 4.2. And this bumps your energy density up to where it's very competitive. So this is an interesting new development being introduced by some of the Chinese companies, and has a lot of potential. And then finally, there's lithium manganese dioxide, which is typically there's two forms of this: LiM and 204 and LiM and 2, and they have different potentials. If you have both, if you go to this higher form, you'll get 4.2 max charge voltage, but it has a very irregular discharge voltage. And it's also it's very safe because the manganese will tend to dissolve at higher temperatures. But, and manganese is cheap, so it's very low cost in that regard. But it does have problems with cycle life, especially if the temperature goes up. But that kind of gives you, I think, a feel for the range of characteristics and for the cathode. The cathode's really the determining factor in the cell energy density. If there's usually a couple times more cathode than there is anode on graphite because it has lower capacity. So here we're talking 145 versus 372 for the graphite, right? So you need a lot more of this stuff to have the energy. Now you have to balance the capacity of the anode and the cathode, and usually you have a little bit of excess capacity in the anode, and that's because when you charge, you're moving the lithium ions over into the anode, and you don't want to have plating, so you want to have a little bit extra capacity over there. So does that make sense?
That's cool. So these voltages, it's interesting to me that the voltages are so low, but I guess when they're making these batteries, these higher voltages, they're just putting them in series or
a cell, like our packs.
They're making a cell.
They're making a pack.
Pack cells.
Yeah.
These are cell level numbers.
That's what I meant. Yeah, a pack.
That's why in the beginning I tried to differentiate cell and pack.
Yeah, I never realized that cells were always the same, like based on, they're obviously very close. They're not all exact, but
they're based on the chemistry.
Yeah.
Right.
So this voltage is determined by the chemistry in the anode and the cathode.
That's really cool.
Yeah. So it's that chemical reaction, and they have different, configurations of the material, and that's what determines where these voltages come from. So they're very fundamental down to the basic chemistry.
Very cool.
So you put them in series and parallel when you make an EV battery.
Mm-hmm.
So you'll stack, and the reason I put nominal voltage here, so if you ever, a lot of hobbyists will get down to designing their own packs, right? And so they'll look at this. For some reason, people quote the nominal voltage, and then they'll stack these up. So if you want to have 100 volts is a pretty typical kind of pack voltage, all the way up to about 400. Well, you can see how many of these you have to put in series to get to that voltage. And then you can see your max charge voltage will be, all of these together. And so that's why it's interesting for those applications. So
the old school 9-volt square battery is actually a battery pack, right? It's got 3 little cells in it.
Inside, there's there's a stack. There are alkalins button cells, and so in a 9-volt alkalin's about 1.2.
Okay.
There's like 7 or 8. I forget the exact number.
Okay.
But if you open one up, that's what you'll find. So that's a pack, right?
Yeah.
Because it's multiple cells inside of it.
And then the old D cells, that's also a battery pack. It's got
that one. I've opened those up.
Oh,
because I get the carbon rods out of the center of those things.
Yeah, they're double A. So the capacity doubles every time you go up a letter. And so the double A, C, D cells, they're all that's the cell voltage that you're looking at. Those are 1.2, 1.5, depending on the chemistry, volts. So for each one, so they're not packs; they're individual cells.
Okay.
Yeah, and that D, I guess it's like something rolled up around this center carbon rod.
Yeah, a thin sheet rolled up.
Yeah. There's different ways of manufacturing them and a lot of it has to do with the internal resistance. You might notice it's interesting. Like I have a key fob for my car, and some button cells, alkaline button cells, will work in it, and some won't. And what the reason is the resistance. And the guys from Duracell told me once they did a very thorough analysis of all the differences between different alkaline cells all over the world, and they're all pretty much the same capacity, but they have quite a bit of variation in internal resistance. So if you ever notice in like your key fob for your car, you can buy little testers that will allow you to test the resistance of these different button cells to tell if they're going to work in certain applications or not, because the cells vary in terms of their internal resistance.
Okay.
So
pro tip, yeah.
Well, the other pro tip I like to give people for lithium ion is if you want to get maximum life out of your cell or your battery, you really shouldn't fully charge it or fully discharge it. And the reason is, let's see if we back up to here. So when you fully charge a cell, you're moving the maximum amount of lithium ions into the graphite that they'll accept. Okay. So what happens in one of the early failure modes in lithium ion is that this graphite in the planes, it can do what's called exfoliation. In other words, when you're moving this lithium in there, you're stressing it, right? And if you have any impurities, you're going to be stressing it more. The more lithium you move in there, the more you stress it. And so if you keep your charge to about 80%, no more than 80%, and you keep your discharge to no more than less than 20%, you're operating kind of in the sweet spot between these two materials rather than stressing. Now, the manufacturer wants to be able to claim he's got real good capacity, so he'll quote the numbers at full charge and discharge. But if you want longer life, charge it slowly so that it allows time for the lithium to move in, intercalate into the graphite, and don't charge it to 100%, or especially don't discharge the cell to 0%. In both cases, you're stressing the electrodes, and so it will reduce your life. Also, don't do the full rate. In other words, when you operate at a real high rate, it tends to stress the material more. And so, anyway, the point is, if you want the longest life, charge it and discharge it slowly, and only go 0 to 20 to 80%. If you look at some of the recalls on electric vehicles, one of the things they'll tell you is don't charge it over 80% of capacity, and don't park next to other cars,
other electric vehicles,
or next to don't park it in your garage.
I wonder if something like that is built, because like a smartphone, it's smart charging, like it's keeping track. So I wonder if it's built in to the systems, or if you can even get control of it. Because I used to load custom operating systems on my Android, and it would have these like really intricate battery controls,
battery management,
where you could tell it, don't charge it over this much, and once it's discharged to this amount, like basically call it dead. Yep.
Well, there is, the smart chargers are basically what there's called a battery management system, a BMS, and it's a chip. They're actually, most of them are made by Texas Instruments down around you guys, and I think TI makes 90% or something at one point of the world's BMS chips, although that's probably changed. But they're pretty sophisticated chips, and they manage this constant current, constant voltage charging. They monitor for overcharge and over discharge, and they'll shut off in either of those cases. And I'll talk more about that in the cell design, to prevent safety issues. And they can also do what's called cell balancing. So when you put these cells in series, if you have one cell that's weak, it can cause the other cells to go over voltage. And so that's another thing that they monitor, especially on charge. So
this
is making so many things make sense right now. The iPhone does this management system, and it'll tell you what it's doing with the battery, like especially if you plug it in at night. So the assumption the phone makes is like, well, you're going to sleep, so here's how I'm going to manage the battery. I'm going to charge for like 6 hours, and then at the very end, I'll like get it all the way to 100%, quote unquote 100%, right before you wake up. Yeah. So the phone is sort of planning how to deal with the battery when you don't need the phone.
Yeah.
Well, so it wants to charge at a slower rate to save your battery, right?
The slowest rate possible while getting it to 100% by the time you wake up.
Yeah. Yeah.
Or, maybe the 100% and the 0 is between the 20 and 80. I don't know, but I'm surprised at how long these batteries my phone battery still operates, I feel like, the way it was brand new years ago. It hasn't seemed to change.
Yeah, I definitely notice with the newer phones that the use time over time does not seem to go down nearly as much as it used to.
Yeah, they used to drop, but you'd have to charge your phone multiple times a day.
Yeah,
I still have like more than half my battery life left at the end of a day.
Yeah,
yeah. Well, back in the early days, the OEMs would specify 300 cycles. Then it went to 500. Now it's up like 1,000. You can get them almost 2,000 cycles. And one of the benefits potentially of solid state batteries is that there are some that I don't know if you've seen micro batteries. People use them in electronics, but those can achieve incredible cycle life. So lithium-ion it's a very long-lived system, and one of the advantages of going to like artificial graphite, high purity, better manufacturing control is you can get much better cycle life. So I was just going to say, so this is nickel, cobalt, manganese, and this is cobalt, this is manganese, nickel, and these are the percentages that you can put in a cell. It just kind of shows the trade-offs you're making. So as you go to more nickel system, that chemically it's a little bit more stable, but it's expensive because of cobalt. When you go to just more manganese, the capacity goes way down and the safety goes way up. That's because manganese is a lower capacity material, but as I mentioned, it has a problem where as you raise the temperature in the cell, it basically will dissolve in the electrolyte. And so from a safety perspective, that's a good thing. From a life perspective, it's a bad thing. And then nickel, which you really see a lot, increasing amounts, higher amounts of nickel, even 95%. Nickel traditionally has been less safe, and there are people trying to make pure nickel cathodes, and solve the safety problems at the same time. So the capacity goes way up as you go to high nickel, but the safety goes down correspondingly. And so that's been a challenge.
It's crazy.
NCM 811, which is 80% nickel, is pretty common now and is a very good performing material. With safety is not. I think they've engineered the material where the safety is better than it was. So talk more about materials, because one thing I want to point out is this is kind of the pie chart of where the costs are in a lithium-ion cell. And it actually now I have more than half the cost. It's actually more like 70-80% of the cost is just the raw materials. So the cathode being the most expensive, and then the other various things, electrolyte, anode, are the kind of make up the rest of it. These things you see here, separator. So this is a problem for the industry because there really isn't any good recycling for these lithium-ion cells. You can't rework the cells. Very seldom can you rework them during the manufacturing process. There still aren't any really commercially viable recycling technologies. I look at it and I think, boy, when all these EVs start getting turned in, what are you going to do with the batteries? There's really, it's a major problem. And then
we could build bombs out of them, right? Just give them to the DOD.
Yep. And then for the manufacturer, it's a problem because when you don't have good yield, well, you have to pay to get rid of your bad cells.
Yeah.
So it's a really big problem. And
somebody will eventually solve it, though, right? I mean,
I would imagine, like
even if we end up with massive piles of old batteries, somebody eventually will figure out how to go in there,
oh my God,
and mine that and reuse it.
Yeah, there's something incredibly valuable that we can.
You know what they do with them now is some of it's just ground up and put into asphalt. So it's down there with Jimmy Hoffa in the parking lot.
Now we know when we're driving down the highway, be like, we're driving on these old EVs.
One day somebody's going to figure out how to charge this road.
It's not exactly an economical benefit. Especially when some of these materials are actually pretty rare in a sense. So this just kind of shows a history of lithium-ion cathode materials. Cathode is the most expensive component. And so the gray is nickel and the green is cobalt. I just find this interesting. It's $1 per kilogram. So back in the 2008 timeframe, it was running around $30, $40 in that range for cobalt. And then when lithium-ion really started to come on, especially with Apple, putting in importable devices. Of course, the market suddenly shot up because everybody thought, oh, this is going to be a huge demand. So it went up to almost 120. And so then the industry panicked and introduced nickel, NCM, nickel, cobalt, manganese. And then we had a huge, the Great Recession, I think it's called. And so prices went back down. Well, then when EVs started coming back on, it shot back up. And one of the problems with cobalt is, by the way, is a lot of it's mined in Africa, in these, they use child labor and things like that. And so that there was a lot of effort on nickel, and NCM and LFP and alternate materials. Nickel has since gone up in price because there's so much of it being used, but it's a really volatile market. This was a one-day change in nickel price back around 2020, I guess it was. Anyway, it just in one day shot up to the record close. So very volatile pricing. And then the other problem is, you have to mine huge amounts of these materials. This is it's from this Thomas Hagen website, and it's a picture of the Atacama Desert in Chile. I think it's up around 10, 12,000 feet altitude. And this is lithium mining. And you can see, like, this is a truck.
Yeah.
And this only produces a fraction of the world's lithium demand. And so then this was out of a benchmark report. And they were showing, well, how many mines are we going to have to build for nickel, cobalt, lithium, natural graphite, synthetic graphite. So, huge amounts, huge increase in mining. Nickel production, is very is not friendly to the environment. Nickel mining, cobalt has all these issues. It's a problem, and when one of the problems with the industry is to try and get better range. They keep going to bigger and bigger batteries. So a Rivian pickup truck has 130 kilowatt hours of battery in it, whereas a PHEV, a plug-in hybrid, is only typically around like 25 kilowatt hours. So you can make 5 plug-in hybrids for every one Rivian. And Teslas typically run up to 90 kilowatt hours. And because of this mining, I mean, all this mining has to be ramped, and it has, huge environmental impact. So in one of these large EVs, I've seen numbers of up to 500,000 pounds of raw ore have to be mined to make one large EV battery.
Wow.
So it's a big issue for the industry.
Well, it would be great.
500,000 pounds.
It'd be great to take this mining to space.
Yeah, that's what I was thinking too.
I'm sorry, what?
If you can get it from, asteroids or something instead of doing it on Earth.
Yeah,
that would be great.
It might be a little pricey, but
yeah, it would be pricey, but that's Elon he has the whole Tesla thing, but he also is doing the space stuff. So I wonder if he's looking at that. That might be.
I think actually, I'm a proponent of going to PHEVs, plug-in hybrids, because there's a number of problems with EVs, or a number of issues that are unsolved. I mean, just look at charging stations. There's not enough charging stations, clearly. And especially for people that live in like apartment buildings, it's a huge problem. Right.
Yeah.
So here in California, there's a mandate, you can only have an EV. Well, there's not enough charging stations.
Yeah.
And there's people that live in apartments. So what are we going to do? Right.
Yeah.
I mean, there's other issues as well.
The rolling blackouts too, like in the when we really need energy in Texas, when it's really freaking cold, they're like, "Oh, sorry, we gotta shut your power out." You're like, "Okay, this is not good."
We do that here when the state starts burning down. But so we'll talk about the common form factors, just kind of as for lithium-ion cells. So initially, it was a cylindrical cell. And as I mentioned, these are the diameter and lengths of the cells in millimeters. Tesla has gone to what's called a 2170, 21 millimeter diameter, 70 millimeters long. These are just kind of pictorials. And then I don't show on here was it 4570? I think I have it on another slide. But it's kind of an interesting cell. So inside of the cell, let's see if I have one here, is what's called a jelly roll. And you can see it's inserted into the cell.
Mm-hmm.
Basically, the electrodes are wound up with the separator in between into what's called a jelly roll. And there's tabs for contact, one on the top, one on the bottom. And that's what you're looking at in these pictures. So in this one here, as you can see, this is a jelly roll sitting in the can. And then there's when you make these, there's what's called a groove made around the top of the lid, and that's what the cap rests on. And cap is really important because it has a number of safety features in it. This is a side view, and this is a side view. I think it's a Sony cell. And in the cap is what's called a PTC, That's a positive temperature coefficient. Think of it like a fuse. It's a temporary fuse. There's a CID, current interrupt device, and then there's a vent. There's 3 different safety devices built in there. And the reason is that you have this steel can pressure vessel. And in a safety incident, you don't want to have that thing turn into a bomb. So one of the devices is a PTC. It's really like a plastic disc that goes in, and it's like a fuse between the positive contact and the cell. And so what happens, the reason it's called a PTC, or positive temperature coefficient, is that as the cell gets hot and, you're overcharging and you're putting too much current into it, this will disconnect due to temperature change, getting too hot. And the idea is it can disconnect the charger from the cell. So this is another thing you might see in a power tool, because if you take and say, it's really hot outside and you really drive your power tool hard, with a lot of power in a closed environment, you might get it so hot that the PTC will trigger. And it'll look like the cell died, because all of a sudden you won't be able to charge or discharge it. Then if you wait, for an hour or two, or, sometimes you'll see it come back. And that's because the PTC has come back to a lower temperature and reconnected. Unfortunately, it doesn't completely go back to its original state. And so the cell won't really act like it did when it was new, but it will still act like a cell. And then we have what's called the current interrupt device. And this is basically, it's called sometimes a frangible tab is the way. The contact from the outside is welded, sort of spot welded to the tab on the jelly roll. And the reason it's done that way is, so for instance, the failure mechanism for lithium-ion is to generate gas, or the failure symptom, I guess I should say, is it will generate a lot of gas. It'll pressurize this can. And when it does that, it pops this. And so it acts like a permanent fuse, because it'll break the connection, the weld. And so your cell will be disconnected completely and permanently.
That's cool.
So, and then finally there's a vent. And so this is a reverse buckling disc, what they call it. So in other words, you can see it's usually stamped. And when the pressure gets too high, typically up around 300 to 500 psi, depending on the vent, it'll pop and vent all this gas. And so if you see videos sometimes of a 18650 going off, it'll spray basically the flammable electrolyte. It'll kind of atomize it into the room, and where it mixes with air. And then essentially you have what's called a fuel air explosive. And if you like explosives, search fuel air explosives, and the Air Force makes some really great ones. Basically, they take gasoline and they vaporize it, up about 1,000 feet above ground, and ignite it. And what happens is you get to the perfect stoichiometry of oxygen to fuel, so that you have a really high explosive, and it makes a wonderful explosive. And I don't have the video. I should have dug it out, but there's some great videos of 18650s doing this. There's one that was taken in a shop in, I think it was in England or something, and it blew the glass doors off the building. Because I've blown up ovens with these things and stuff like that, because when you get this mixture, it's very explosive. So these are the devices that are trying to prevent that, the various safety devices. But, they don't always work right. You can get, sometimes there's so much gas generated instantly. So, these safety events occur. They're called thermal runaway because they occur so quickly, and basically generate a huge amount of flammable toxic gas almost instantaneously. And if you plug this vent or, things like that, then the cell will just explode. So,
Wow.
Jeez.
this is what you guys are making down in Austin. It's a 4860 cell that Tesla's making out in their facility. 48 millimeter diameter, 60 millimeters long, 25 amp hours. A mistake, there should be amp hours. Whereas a 2170 is on the order of 5 amp hours. So it shows you how they're scaling up to these much bigger cells. Then there's what are called prismatics. These are heavily used now. This form factor is heavily used in China in like electric buses and cars. It basically, the prismatic just means it's kind of a square form factor. This picture over here, it's got a flat jelly roll. It's wound around a flat mandrel. And so there's a pressure vent, and then, like a burst disc in a cylindrical. There's not the same safety devices usually on these cells. Very often they're put on the BMS board, so things like the PTC.
What's the BMS board?
What's that?
What is the BMS board? I guess I forgot that one.
Battery management system.
Oh, yeah.
Remember we talked about the charge discharge. So where you see prismatics mostly these days, these small ones is this like this. This is a small prismatic. You can see kind of the form factor.
Okay, yeah, GoPros have those.
What's that?
GoPro cameras have those, the little square one, yeah.
Yeah, sometimes it's just a pack with a pouch cell inside of it. It can be plastic. You don't see these as much as you used to, but what you do see now are these large prismatics. This is a 25 amp hour one out of a Ford, and these are popular in China because they pack very well to make a big battery pack. You just stack them next to each other to run the bus bars, so you get very good volumetric packing.
There's no loss of space where you're packing cylinders in a square. Yeah. You got all these voids.
Yep, that gives you. And then there's finally what are called pouch cells. This is principally what we make here at SpectraPower, and so you'll see a lot of different terminology: soft pack polymer, which is kind of a misnomer; laminate, different names for them. And they can be made in two versions. One is a flat wound jelly roll, like a prismatic, or they can be stacked, where the electrodes are stacked one on top of another. Winding is faster, so stacking can give you a little bit better performance, but it's slower to do. So we make small quantities. We use stacking.
Is this what they use in like tablets?
Yeah. Yep. And like in an iPad.
Yeah.
Yeah. So they're you can make very thin, large form factor cells. This is a max cell. And those are the two mechanisms that you can use. Pouch cells, well, we'll talk, let me see this. So this is a comparison. So cylindricals, they're great for high-speed manufacturing because you can wind them really fast. Over 30 parts per minute you can wind. And they give you really good compression of the rolls because, think of the old Chinese finger puzzle. You can wind these really tight, right? Very high pressure. And you don't have to, use any kind of external compression. So they're very good for that. Actually, some of the best cycle life numbers you'll see are in cylindricals. But what are the disadvantages? Well, fixed form factor. Like I said, the old laptops were thick because they had to use these 18 millimeter thick cylinder cells. The cap is complex in the cell. You have to tool each can, which is expensive, and it's fixed. You can't change it. And then, like I said, it's a pressure vessel, so safety is always a problem. Prismatics, so you get battery pack density. That's like we were just talking about there, you can see. Heat dissipation is better because it's a flatter form factor. That's one of the problems when you have a very big cylinder. It's getting the heat out. From a thermal perspective, if you think about it, the jelly roll has wound plastic sheet, which doesn't, conduct heat, and the electrolyte acts more like almost an oil in terms of impeding heat transfer. So when Apple first went to some bigger cells, this 26650 back in the day, they had cells exploding because Sony hadn't really quite figured out the heat dissipation in the large cells. Yeah, so it's just like airplanes, right? It takes a while to figure it out. In between, you have a few accidents. So that's those advantages. They're slower to wind because you have a flat mandrel, and I can talk about that more. You don't get the high compression because it's a flat pack, and you have to laser weld the cap. Cylindricals, typically the cap is crimped, although you can laser weld them. But laser welding is more expensive. But in a prismatic, you don't have a choice. You really have to laser weld it. And then there's pouch cells. And so it's got a very thin form factor. They're a little bit more expensive because they're slower to make. And the reason pouch took off was Apple was actually the first company to introduce it, because Apple usually gets a little bit more money for their products, right? And because it's sort of a premium product. And so they introduced pouch cells starting in iPods, then in the iPhone 1. And that really brought pouch cells into the mainstream, because before that it was mostly cylindricals. They really dissipate heat well because they're very thin. You can make them they're very easy to change the form factor. That's why we make them here for people, experimenting with different materials for their batteries. You can laminate them, the electrodes together easily, so that sort of like you would with a sheet of plywood. You can put a coating on the separator. It's usually like a PVDF or something that will allow you to heat it and compress it and causes the electrodes to be laminated together. You can change the tab size, so if you want to have high power cells, you can put wider tabs in. And then for safety, I think they're about the best, because the pouch will vent typically somewhere less than 100 psi. It'll start to vent. So instead of like a cylindrical, which if it plugs up, it can go up to 1,000 psi before it explodes, this will vent. You still have some of the safety issues, but not as violently. Disadvantages: it's more expensive. It can swell if you have problems. It'll puff up like a balloon, and you have to do what's called vacuum degassing when you're manufacturing to suck all the gas out of it. So that adds cost. And like I said, you may have to clamp it to keep it from compressed, depending on what kind of technology.
Yeah, I think I saw somebody post somewhere online, like they were charging their laptop and they were like, "Is this bad?" And there was like these bubbles on the bottom. Like, yes,
very bad. Throw it in the pool and wait.
When you see swelling and stuff like that, that's a dangerous cell.
Yeah.
Get that thing far away from you.
Yeah.
Don't leave it charging in your house. Things like that. One of the problems with lithium-ion is that it can explode spontaneously, and that's due to these manufacturing defects. Fortunately, they're very infrequent, but they do happen.
Yeah.
And so, all of these safety incidents that I showed you, the bike and the buses, those were spontaneous, usually under charging, but it wasn't like an abuse. Somebody didn't crush the cell or, overcharge it. So that's one of the problems. So,
wow.
So I don't know, guys, how are we doing on time?
Well, whatever is good for you. I mean, we can take another break if you want.
2 hours. It's great, but you can keep going.
Well, I'll say a couple words about manufacturing and we'll wrap up.
Okay.
So this is a quote from Elon Musk. which I agree with wholeheartedly, having done it. It's the hardest thing in the world.
Mass
It is
producing them.
really hard. I want to emphasize. Never thought it would be as hard as it turned out to be. And this is very, very true. Prototypes are easy.
Yes.
And so this goes back to what our friend Thomas Edison said. People will produce a prototype. They'll make maybe 50 or 100, few hundred. And that's completely different than trying to make, millions or hundreds of millions of cells. It's night and day. You can't compare the two at all.
Wow.
And so people will cherry pick a few cells and say, "Oh, I've got this really great cell," and they'll never manufacture it. This manufacturing was developed by Sony back in the 80s, and it really has not changed very much up until today. And the reason is that it's very difficult. And so one of the things I do have to give Tesla, credit for is that they're really the only U.S. manufacturers of lithium-ion cells at this point. I mean, they're the only U.S. company manufacturing lithium-ion in the U.S. And they've actually introduced some innovations that you'll read about. One is the dry electrode process. That's very tricky, could have great benefit. Those kind of innovations are very hard to do. And I think the fact that they've taken it on and are having success is very impressive. So kudos to Austin.
Awesome, man. That's cool.
So I'll just give you a few words and maybe I'll run one of the videos. And so there's really three major steps. You make the electrodes that go into the cell, and then you assemble them into a cell, and then you do what the formation, aging, and test, which is the final part. Each of these is very different skill sets, different problems. That's one of the things that makes it hard. So electrode making takes just as a very round number. It's like a day. So you have to make the binder that holds the electrodes together. It's basically a plastic binder. Then you have to make a slurry. You have to coat it, and then you have to compress it with a roll press, a calendar, and then you have to slit it to the size you want. Cell assembly, think of that as another day. So you wind or stack, like we talked about. You have an insulator you have to put down to in the cell. You have to fill it with electrolyte, and you have to seal it. And then formation and aging can take 1 to 2 weeks. Back in the day, Sony would do it for 3 weeks. And the reason you do this aging is you charge the cell. Remember, they're built discharged, so you charge it, and then you store it. This is where battery factories typically burn down, and almost everybody has had a fire. And it's because in aging, your reason you age the cell is you want to let any internal defects show up, and usually they show up by exploding or catching fire. And so, when we were manufacturing cells here in Livermore, it wasn't unusual for us to have 1 or 2 cells blow up, in the aging racks. And so you usually would have some kind of fire suppression. Then you do a voltage and impedance check, and you sort the cells according to capacity and impedance. This is a pictorial. So this is just mixing the slurry, and you coat it. You use either a reverse roll coater, it's called, or a slot die. You cut it to the size you want if you're stacking. You roll press it through these calendars, and then you slit to the width and exact size you want in the cell. This preparation of bare part is where you have to clear an area off of the coating to get to the metal so you can tab to it or weld to it using an ultrasonic welder. And then you take the positive, negative, and separator, and you wind it up into the jelly roll. Here's a flat one, and then you have 2 tabs sticking out of it.
Wow.
You put it in a can and weld the tabs and seal the lid, usually with a laser welder, after you filled it with electrolyte, and then you're ready to charge it. give some pictures. This is out of our facility in Livermore. This is a coder. This is what we call this is really kind of a prototype pilot coder. The big ones look like this down here. This is a guy standing on the catwalk.
Wow.
So these things are huge. This is a coating head of a slot die coder in China. And this is the there's a beta gauge. It's called to check the loading, how much material you have on the electrode. This is what a roll press and slitter looks like. This is so you after you compress and slit the material, you take it. In this case, we took it through a vacuum oven to dry it, and then this is for production scale. These are pilot scale. This is a roll press. You can see the width of the electrode here, and this is a density monitor, and this is the drying ovens after it's been slit. This is what the winders look like. We had 4 of these winders. They were made by Sony. They're about $1 million each back in the 90s. And this is for winding prismatic jelly roll. They're very sophisticated machines. That's why they're so expensive. And this is the grooving machine. This is a facility in China. And this is kind of interesting. You can see the X-ray inspection of the groove. And that's important because if you have to do a lot of preventive maintenance in lithium-ion plants because the equipment is wearing. So in this case, the grooving tool can wear, which will cause you to not have enough of a groove or to have a too much. In which case, if you have a safety incident, it'll just blow the cap off of the cell. And then this is cylindrical electrolyte fill. You can see it's a big rotary dial. Filling is kind of a problem for lithium-ion because they're so densely wound. And so what happens is you pull a vacuum on the cell, and you inject electrolyte, and then you let it sit. You only inject about a third or half. It goes around this dial, which just takes time, and then you fill it again. And so you may have to do that 3 or 4 times. Mm. This is an automated cap assembly machine that we had for prismatic cells, just to show you the kind of level of severity. This is just to make caps for the cell. And that was a pretty simple cap. This is a little video I'll show you from our production line.
Welcome to Poly Store's manufacturing facility in Livermore, California, just minutes north of Silicon Valley, the only one of its kind in North America. Poly Store is the first in the world to use high-capacity lithium nickel cobalt. High-volume roll-to-roll coating equipment mass produces the electrode material at high yields with low costs. Electrodes are coated and compressed for maximum packing density. A slitter cuts the electrode materials to exact dimensions. The electrode materials are now ready for the assembly line. Using state-of-the-art winding equipment, the positive and negative electrodes are wound into a core.
Oh man, that's cool.
Then, the jelly roll is automatically assembled into a complete cell. Each cell assembly line is capable of producing 8 million cells per year. A header is fitted onto the cell and laser welded into place. Liquid electrolyte is injected into the cell. Cells are then sealed with a final weld. Cells are washed, X-rayed for QC, shrink-wrapped, and lot-coated. Cells are now ready for charging. Using a process called formation, the completed cells are charged and tested. PolyStore's formation process ensures worldwide shipments of the highest quality lithium-ion cells.
Okay.
Man, that's some incredible equipment.
Yeah.
We work in a winery, so we use some automated like bottling equipment and stuff like that.
Nothing compares to that. Yeah.
No, that's insane amount of.
Yeah, we always used to say that Livermore's two big products were wine and batteries.
Yeah. We also have to age ours, but we don't have to worry about it exploding usually.
Yeah.
Not usually.
But it takes a year.
Yeah.
It'd be great if we could age it for
the
2 weeks.
similarity is that when you make a battery, you seal it up. You fill it up with chemicals and you seal it, right?
Yeah.
And you're done. You can't open it. You can't change it. Yeah, just like wine, you put it in, you seal it, and the batteries in the wine. I mean, our batteries have outlasted most wine, I think. So just to give you an idea of scale, this is a gigafactory in China, and I kind of like this video, so you get a kick out of it.
All right.
If nothing else, the music is good.
We can't hear it.
Yeah,
it's all right, but
Oh, you can't?
I think
Okay,
it's being
sorry.
squelched out.
Yeah.
It's okay.
Wow.
Mixing.
So,
Coding. And are they doing all this in the equivalent of like a clean room?
it's a dry room.
Dry. Okay.
Yeah, but there is some cleanliness.
Man.
Now, what are the relative size of these cells that we're looking at here?
You'll see in a second.
Okay.
They're 60 amp hours. Prismatic. That's your jelly roll.
Yep. It looks really complicated.
Yeah. Now there's the laser weld.
Yep.
Jeez.
God. Yeah. Equipment in there is just. Holy crap. Okay, those are pretty big.
What is happening here? I don't understand. Formation.
So this is automated formation. So remember I said one of the last steps is you do the first cycle charge on the cell.
Yeah.
You build it, discharge, and then you're going to charge it once you've finished building it. And it's a slow process at usually about 20-hour charge time. And you're forming what's called the SEI layer. I mentioned the solid electrolyte interface fiber on the carbon. That's actually critical for safety. So then they're being put into these racks after they're formed and they're aging. So this is usually where fires happen. And there's a fire suppression system in these racks as well. But
wow, so they have all this stuff automated. That's crazy.
Yeah. See, there's very little. Actually, the labor is one of the lowest parts of the cost of a lithium-ion cell. They do this mostly for quality, because handmade lithium-ion cells tend to be more dangerous, less, poor. The life isn't as good, and things like that. Because it's kind of a precision assembly, but that's why this is so hard to do. It isn't just this. It's the. Let's see if there's one more. So when you introduce a cell, like a new technology or even a change in a cell, this is just kind of the process you have to go through. So you have to go through what the preliminary PDR cell design review. And then you'll build prototypes, a few hundred, takes you about a month. Then you do testing, takes you about a month. If it fails, you go back, change, start over. Then if you pass this, then you do safety testing. If it fails, you go back, change, start over. And then you go into cycle life testing, which can take you several months. And if that fails, then you go back, you change, you start over. And then you finally go into CDR, critical design review. If you fail, you start over. And then you send pre-production to your customers, and that takes about a year. And if it fails, you start over. And finally, you're ready to release to manufacturing. It's a very difficult and expensive.
Wow. So this is because we've talked about this a lot about how, I think differently now that I've seen this, but how it seems like our battery, what am I trying to say? Our development or advancement in battery technology is so slow. And this is part of the reason why. But
yes, yeah, it's hard too. I don't know how to quite describe it, but there's so many kind of interacting parts. You saw the level of sophistication of the equipment.
Yep.
The equipment is very important. If you get a bad piece of equipment and you have to change it, can take you a year. And then cycle life testing. Remember, these are rechargeables,
right.
And so the OEMs like Apple are saying, "Oh, well, we want 1,000 cycles." It takes months to even test, and if you have a problem and you have to change it, you have to go back and fix it.
Wow,
it's a very slow, painful process. That's why this, valley of death. So your burn rate is just really high before you even get to ship a product.
Yeah.
And the other thing is you saw the aging racks. Well, you buy all these materials, and most of the cost is in your materials. And then it takes you, a week or so to make a cell, and then you put it in aging, you form it and age it. You have millions of cells sitting there doing nothing except costing you money. Where you can
catching
sell
on
them.
fire
and then burning each other down.
Yeah, and a few of them are burning themselves up, and so it's a very difficult thing. That's why there's so few manufacturers here. They're almost all foreign.
So it's the valley of death, which makes it so difficult to advance.
For new companies,
yeah,
or even for a company that's investing. You're going to invest, and it can be, years before you see a profit come out of it.
Right.
And usually when you start up this line, the yields are terrible. And remember, you can't salvage or recycle the cells. So all that materials that you spent money on is down the drain, and you have to pay to get rid of it.
Yeah.
It's a very painful process.
So So before we wrap it up, can I ask a speculative question? We've discussed this before, but like we've talked about in this episode how batteries are kind of like a bomb, right? So one thing that happened with bombs is to get much greater power out of them, they went nuclear instead of chemical. Is it possible that we will eventually have something like a nuclear battery?
Well, the closest thing, there are some portable reactors that the military made, but the problem is the energies involved are, to get a nuclear reaction and to control it are much more difficult. There are a lot of, at Lawrence Livermore Lab, they demonstrated scientific break-even at the National Ignition Facility, which I think is like one of the major scientific milestones of our era. That's something that has only been dreamed of. Very, very difficult to do. I've been through the facility a couple times, and there are some startups now because of that. There's been more investment in nuclear energy, and I'm a very firm believer in nuclear energy. I think these ideas of relying on solar and wind and stuff are great, but they're not going to get us there.
Yeah.
One of the problems with EVs, they don't want to have nuclear power. So, California has a restriction on how much solar you can use because it's so disruptive to the grid. They limit it to like, I think 20-30% max. And they've actually had power stations blow up, because, a cloud goes over, and you lose your solar power, and it really it damages the grid. So nuclear is a stable, reliable source. You go back to like 3 Mile Island and all that stuff. That stuff's ancient history.
Yeah.
Yeah.
There weren't even cell phones back then. I don't know if, younger people can sort of grok it, but there's, that technology is back in the era of, I don't know, the invention of flight or something.
Yeah.
Anyway,
one of the great points I've heard about nuclear is that there's like, they have nuclear submarines. They don't melt down, and they're run by a bunch of 18-year-old dudes.
They last a long time.
They last forever.
No, I think the environmentalists have really steered us in the wrong direction. Look at Germany. They shut down all their nuclear plants, and now they're like, oh gosh, what are we going to do?
Yeah.
And you look at California. Newsom had to step in to Diablo Canyon and say, oh, we're not going to shut it down because we wouldn't have any power. So we're actually very reliant on it, and to charge all these EVs, that's a huge problem, right?
You definitely want to charge them with nuclear
power in a clean, way. So anyway,
well, I heard you said grok. Are you a Robert Heinlein fan?
It was a long time ago.
Yeah, you remember in his stories that the shipstones were nuclear batteries.
Yeah,
that was the first time I read something. I was like, man, this would be great if you just have this block and you put it in your car and it runs it for a year.
Yeah. Well, it's become, I don't know. I think everything, things like 3 Mile Island threw it all off the track, and there are many new technologies in nuclear, and I think we really should be investing much more heavily in it.
Well, I hope so.
Yeah. Well, this is fascinating.
Yeah, man.
Thank you very much for taking the time to educate us on this. That was awesome.
Good. Hope you enjoyed it, and you guys have a great day. Let me know if anything else, you questions or stuff pop up.
Okay. Thank you so much.
Okay. Thanks. Let me see if I can get out of here now.
Go watch Chernobyl, folks. It's never going to happen again.
Okay.
All right. Thanks so much, buddy.
Yeah.
Bye.